Every time you land on a commercial aircraft, hydraulics saved your life at least 3 times. When the pilot lowered the landing gear, hydraulics. When the brakes brought you to a stop, hydraulics. When the flight controls kept the aircraft stable on approach, hydraulics. And most passengers have absolutely no idea any of this is happening. By the end of this video, you will. So what exactly is a hydraulic system? At its most basic level, it's a system that uses pressurized fluid to generate force and movement. The principle comes from Pascal's law. Pressure applied to a confined fluid is transmitted equally in all directions. In simple terms, you push fluid down one end of a pipe, and something moves at the other end. Aircraft hydraulic systems operate at extremely high pressures, typically between 3,000 and 5,000 pounds per square inch on modern commercial aircraft. That's enough pressure to move massive flight control surfaces, retract heavy landing gear, and bring a 300-ton aircraft to a stop in less than 2,000 meters, all from fluid in a pipe. Every aircraft hydraulic system has 4 core components. First, the reservoir. This is where the hydraulic fluid is stored. It's not just a tank, it's a pressurized vessel that ensures a constant supply of fluid to the pumps under all flight conditions. Second, the pump. This pressurizes the fluid and pushes it through the system. Most aircraft have both engine-driven pumps and electric pumps as backups. Third, the actuator. This is where the hydraulic pressure becomes physical movement. Push fluid into an actuator, a flight control surface moves, a landing gear retracts, a brake applies. Fourth, the return lines. Fluid that has done its work returns to the reservoir to be used again. It's a closed-loop system. Continuous, reliable, redundant. Let's start with flight controls. On a commercial aircraft, the pilot doesn't physically move the control surfaces directly. The forces involved are far too large for that. Instead, the pilot inputs a command, and hydraulic actuators move the surfaces. Ailerons control roll, elevators control pitch, rudder controls yaw. On modern fly-by-wire aircraft like the Airbus A320, the pilot's input is converted to an electrical signal which commands a hydraulic actuator, which moves the surface. The pilot never physically touches the surface. Hydraulics do the work, every input, every maneuver, every flight. Without hydraulics, a commercial aircraft cannot be controlled. That's how fundamental this system is. Landing gear. One of the heaviest, most mechanically complex systems on any aircraft, and entirely hydraulically operated on commercial aircraft. When the crew selects gear up after takeoff, hydraulic pressure releases the uplocks, pushes the gear into the wheel wells, and locks it in the retracted position. When the crew selects gear down, hydraulic pressure releases the downlocks, extends the gear, and locks it in the down position. The whole sequence takes approximately 10 to 15 seconds. Now, what happens if hydraulics fail? Most aircraft have a gravity extension system. The uplocks are released, the gear falls under gravity, and locks down mechanically. No hydraulics required. The system is designed so that the safest state is gear down, even without power, even without hydraulics. Brakes. This is where hydraulics arguably have the most direct impact on passenger safety. Aircraft brakes operate on the same principle as car brakes. Hydraulic pressure forces brake pads against a disc, creating friction, slowing the aircraft. But the scale is completely different. A commercial aircraft landing at 150 knots, weighing 200 tons, needs to stop in less than 2,000 meters. The energy involved is enormous. Modern aircraft have auto-brake systems. The crew selects a deceleration rate before landing, and the system automatically applies the correct hydraulic brake pressure to achieve it. There are also carbon brake assemblies. Extremely high performance, extremely high temperature. After a heavy landing, brake temperatures can exceed 500 degrees Celsius. As an AME, brake condition and hydraulic brake pressure are checked on every turnaround, every single time. So what happens when the hydraulic system fails? First, it's important to understand that commercial aircraft have multiple independent hydraulic systems, typically 2 or 3. On an Airbus A320, there are 3 systems: green, blue, and yellow. Each one can operate critical flight controls independently. If one system fails, the others take over. If 2 systems fail, there are still options. The aircraft is designed so that no single hydraulic failure can make it uncontrollable. But failures do happen. Low hydraulic pressure, fluid leaks, pump failures. These are the kinds of defects we find during walk-arounds and scheduled maintenance. When we do find them, the aircraft doesn't fly until it's fixed or deferred under the MEL. The system works because people like me make sure it does. As an aircraft maintenance engineer, hydraulic systems are part of my daily life. During a walk-around, I'm checking for fluid leaks, blue or red staining around actuators, pipes, and connections. I'm checking fluid levels in the reservoir. I'm checking brake wear indicators. These are not routine checks in the casual sense. They are safety-critical inspections that directly determine whether that aircraft is airworthy. When I find a hydraulic leak, I don't guess. I consult the aircraft maintenance manual, I identify the source, I assess the severity, and I make a decision. Fix it before the next flight or assess whether it falls within MEL limits. That decision has consequences for the aircraft, for the passengers, and for me personally. Because my signature goes on the release to service. Here's what I want you to take away from this video. Hydraulic systems are invisible to passengers. You never see them, you never hear them, you never think about them. But every single flight, they are working constantly under enormous pressure, moving surfaces, retracting gear, stopping the aircraft. The engineering that goes into designing, certifying, and maintaining these systems is extraordinary. And the people who check them before every flight, the AMEs standing under the aircraft at 2 a.m. in the cold, they take it seriously because they understand what's at stake. Every check, every inspection, every signature, it matters. So now you understand how aircraft hydraulic systems work and why they matter every single flight. If this gave you a new appreciation for what goes into keeping an aircraft flying, hit subscribe. I break down aviation in a way that actually makes sense. See you in the next one.